So we're at the last topic, electrochemistry. Before we formally start discussing this particular branch of chemistry, we'll do well to review redox reactions because it's a prerequisite that you are able to balance redox reactions in order to perform the tasks that we're going to be doing in electrochemistry. So I'll remind you of what a reduction and an oxidation is, and then I'll show you two ways of balancing reactions. So in a process like this, which technically speaking can be regarded as a single displacement reaction, you technically have the following fragments. On the one hand, iron 3 plus is turning into iron 0, and on the other hand you have magnesium 0 turning into magnesium 2 plus. So you have two processes going on. Iron 3 plus turning into iron 0 requires 3 electrons being acquired per iron center, and we call that the reduction. On the other end, magnesium going from 0 to 2 plus requires the loss of 2 electrons, and that is what we call the oxidation. Now that is per magnesium center. If we multiply the ratio right here, the 3 electrons per iron, by the number of ions that we have present, which is 2, and over here if we multiply the negative 2 electrons per magnesium center multiplied by the actual number of magnesiums, which is 3, this tells us that we are either losing 6 electrons or we're gaining 6 electrons. In other words, the total number of electrons is constant in this entire setup. So in essence, the electrochemistry process is going to be one in which we balance the number of electrons lost in the oxidation step with the number of electrons gained in the reduction step, and you're going to have both of them playing a role in each one. So let's talk about electroreduction potential diagrams. This is the part that you haven't seen. This is the new part, which I'm going to introduce you to right now. But pretty much for whichever element you're looking at, you can take a look at the potential charges that our element can acquire. In essence, the potential redox partners that an element can have. And the way you read this diagram, at the top is the most oxidized species, and as you scan your way down into the diagram, you end up going into more reduced and more reduced species, with the most reduced species present at the very bottom of the diagram. Now the interface that separates species is the place where the redox potential and the actual redox reaction takes place. Specifically, going from top to bottom represents a reduction. So in this case, that would mean that H plus is acquiring electrons to turn into H2. And here simply you have to balance your half redox reaction to come up with the proper reduction. Now here's some idea. You have H2 acquiring electrons to produce the hydride product, which is the most reduced version of hydrogen. And you still have to balance the equation, so you have the proper number of electrons, the proper number of charges, and the proper number of atoms on both sides of the equation. Now, one thing that I'm going to point out in the next video, in the next lecture series, is that the reduction potential is technically a value in voltage that basically kind of creates the boundary between the oxidized species and the reduced species. Values that are higher than this boundary ensure that you stick with the most oxidized version. Values that are lower than this number ensure that you're dealing with the reduced version from the point of view of the boundary. Alright, so those will be the reduction values. So both of these reactions are reductions. Both of them are given in terms of voltage. And the idea is that as you end up dealing with more reduced species, the electric potential is going to become more negative. With 0, which is the reduction potential of hydrogen, of H plus going into H2 being the standard, the benchmark, and we are going to base everything on this specific reduction. You also have the same idea for second row main group elements. One of them is oxygen. And once again, on the very top you have the most oxidized species, on the very bottom you have the most reduced species. And in addition to that, in this particular example, you have this red box to the right of it in between some of the boundaries, and this represents a metastable species, hydrogen peroxide. A species that's not something you can store for prolonged periods of time. Certainly you can't store it for prolonged periods of time if you keep it exposed to light or exposed to heat. So you have to keep it in a cold place that is free of light, because it's that unstable. But what happens with these species is that they actually react with themselves to undergo auto-oxidation and auto-reduction. So the H2O reacts to give you literally the species that is above the boundary in which you see them placed, and also the species that is below the boundary where you see the red box located. So pretty much what happens is that in terms of the oxidation, H2O2 makes O2, produce 2 protons and also 2 electrons, and that's the oxidation event, which is you going towards the top portion of the diagram. But then you also have a reduction event which requires acquisition of electrons and formation of water. So that's kind of what's going on here with the metastable species. And we're gonna see, how they play a role in terms of balancing reactions. Now I'm gonna show you and introduce to you the different elements. As you are well aware, we have a periodic table which has a specific arrangement of the elements. And normally, when we encounter electrochemistry chapters in books, you're given a table with electron potentials going from the most positive to the least positive. And the problem with that is that the elements are not arranged in a particular order corresponding to the periodic table. So instead of doing that, I have preferred to look at each individual row of the periodic table to present the elements with the electron reduction diagrams that I show you for hydrogen and oxygen. So for instance, looking at the second row of the elements, I have literally arranged the elements in that order from hydrogen, well technically from lithium up until neon. And I'm showing the electropotential diagrams for each one of them. So this actually gives you a much easier way to locate the atom just by looking at the periodic table. And so as you can see in the second row, you have different potentials for the different elements. You form different species, and some of them, like nitrogen, actually has a multitude of metastable species that can be formed. The same thing is true for the third row elements. You can arrange them in in that order. And by the way, I'm keeping hydrogen here on the very left side as a reference, just to give you an idea of how negative a potential you need to make to get some of the elements in the reduced state. So yeah, you can see here pretty much the same idea as with the second row elements. The fourth row elements, you have pretty much a similar arrangement, a little less metastable species present. Same thing for the fifth row, main group elements, and also for the sixth row main group elements. So you have all of this in this particular lecture, and I'll probably be providing you with these diagrams for the exam as well, so you don't need to necessarily memorize any of these values. I've also taken the liberty of applying the diagrams for the transition metals. So here's the first row of the transition metals, and here's the diagram that depicts the transition metals. So you can see the different species at the different oxidation states. Some of them are metastable, like in the case of chromium, manganese, cobalt, and copper, but most of the other species look pretty on point. I have also the diagrams for the second row transition metals, which contain a little less metastable species, and the diagram for the third row transition metals, which contain, a similar number of metastable species as the second row transition metals. Just for completion's sake, I've also included the diagrams for the lanthanides, which show a little less variety in terms of the number of redox events that can be obtained per element, and also of the actinides, which show a little bit more variety and a little bit more charges, especially for uranium, neptunium, and plutonium. So all in all, we're going to use these graphs to derive half redox reactions for each event, and as you'll see in future lectures, we're going to put together a full balanced equation, and you'll be surprised at how good you're going to get at preparing your half redox reactions and deriving your oxidation states, your reduction states, putting them together, and performing the tasks that I'm going to have you do for this chapter. But that's the story for the elements. In the next video, what I'm going to show you is the balancing process for the reactions, and I'll be showing you two methods of achieving this. So see you in the next video.